Welcome to Lesson 3D, Combustion Part 1. First, we're going to talk about stoichiometric combustion and then emission factors from combustion. So I want to first define stoichiometric combustion, also called ideal combustion. It means that every kilomole of carbon in the fuel, which is combusted, produces 1 kilomole of CO2 in the exhaust. So all the carbon in the fuel is converted to CO2. That's what ideal or stoichiometric combustion is. Let's look at natural gas as an example, and we're going to do some EFs later. But first of all, I just want to look at stoichiometric combustion of methane instead of natural gas. So methane is burned in simple dry air, and we want to solve for the molar coefficients for this combustion, assuming stoichiometric combustion. So here's the assumptions and approximations. All the carbon in the fuel gets converted to CO2. That's what we mean by stoichiometric or ideal into the exhaust gases. And then I want to define simple air, or also called simple dry air, which is air that has no humidity, but instead is made up of 21% oxygen and 79% nitrogen. If you think about it, then the ratio of N2 to O2, so the number of moles N of N2 to N of O2 would be 79 over 21, which gives you 3.76. So that's why we have this 3.76 in here. This is not just oxygen, but it's air. So we can come up with this chemical equation here fairly simply then. We say CH4, that's methane, plus A, this coefficient, these are all molar coefficients, times air is some other coefficient B, CO2, and then some other one for water vapor, and then nitrogen kind of just comes along for the ride since it doesn't interact with anything. This is ideal or perfect combustion. In non-ideal combustion, you'll get some other stuff in there. Your fuel won't be perfectly pure. You'll get some sulfur perhaps, and then you'll have some nitrous oxides or NO2, etc., that come out of that if you don't have complete pure burning. Natural gas, by the way, is mostly methane. Let's figure out how we can do this. This is a review of what you've done previously. So let's calculate these coefficients, these molar coefficients. You take each of the elements and work out the algebra. It's stoichiometric, so all of the carbon here has to go to CO2. So there's no other molecules in here that have carbon in them. Therefore, for ideal or stoichiometric combustion of methane and simple dry air, we have this solution, which is our final answer. And note that all of the carbon in the fuel has been converted to carbon dioxide in the products. Let's have another example here. We want to estimate the combustion EF, the emission factor, from this basic chemistry that we're doing. We have natural gas burned in a power plant with no APCS, and the exhaust gases go up the stack. I give you the temperature and the pressure, which we'll need later on. Assuming stoichiometric combustion, let's estimate a number of things here: the mole fraction, the mass concentration, and the molar concentration of CO2. So we're concerned about this global warming gas, CO2. So suppose in this problem you're concerned about climate change and global warming. So we're looking at this greenhouse gas CO2 to figure out how much is going up the stack. So let's estimate the EF of CO2 by burning methane, and then compare with EPA's published EFs for burning natural gas. Natural gas is mostly methane, so this should be a pretty reasonable agreement. So let's go through the math. We had this equation from the previous example, and again, this is stoichiometric or ideal, so we've converted all the carbon into the products. Let's look at mole fraction first. Why CO2 is defined by definition, this is a lot of review again, N CO2, number of moles of CO2 over number of moles of total, in the exhaust. And what is the exhaust? Well, this is the exhaust. And remember, these coefficients here were B and C and D. So in terms of the coefficients, this would be B over B plus C plus D. And now plug in the numbers and we get our final mole fraction for CO2, 95,100 ppm, which is pretty high compared to what's in the atmosphere, which is only about 410 ppm. So that's a lot of CO2 that's produced. Almost 10% of the exhaust gas is CO2. Now let's look at mass fraction. Recall the mass fraction of some species is just the mass of the species over the total. So we have here FCO2 is MCO2 over MT, and we can rewrite that since the mass is NCO2 times capital M molecular weight. We can do that on the top and the bottom, NT MT. Notice that NCO2 over NT is what we defined as YCO2, which we happen to have just calculated. So I'll just leave that in variable form, YCO2 times MCO2 over MT. Again, review MT, the total molecular weight, is sigma of YJ MJ. I'm not going to go through all the algebra, and this will be a good review problem for you if you want to plug in everything and calculate F. So my final result is the mass fraction of CO2 of the exhaust gases is 0.151 kilogram of CO2 per kilogram of total exhaust. So about 15% of the exhaust by mass is CO2. Now we need to do mass concentration and molar concentration. So I would strongly encourage you to do this on your own. This is, again, I'll review just conversions between mole fraction and mass concentration and molar concentration. So work on that on your own, and I'll just give you the answers. And if you have any problem coming up with that, please ask me. So by the way, this squiggly line arrow here, when you see that, that means there's lots of algebra that I left out. But here's the answers to 3 significant digits: the mass concentration and the molar concentration of the CO2 in the exhaust. Now let's look at part B. Let's estimate from our chemistry the emission factor of CO2, and then we'll compare with EPA's published EFs. Let's define our EF as the mass of CO2 emitted per mass of fuel burned. So this is how we're going to define our EF. And the algebra here is very straightforward because it's really the same as what we did previously in part A when we looked at the mass ratio of CO2 to exhaust gases. Here we're looking at the mass ratio of CO2 to the CH4, the methane. But it's the same equations, namely here. So REF is just this mass ratio. We just use the N times M for each of these, top and bottom, and we plug in the values here. And so our EF is simply 2743.3 kilogram of CO2 per megagram of CH4. So to 3 digits, I'm going to write this as 2740 kilograms CO2 per megagram CH4. So I typed all this up since it was the same thing we did before, just with a different denominator. So I'm going to call this EF hours. This is what we calculated, hours, and that's our value then, our EF that we're predicting. And let's compare it to EPA's published EFs. Now I found 3 of these in various units. So this one is in terms of kilograms of CO2 per 1,000. Remember, SCF, standard cubic feet of natural gas. So this is a volume of natural gas. Here we have in terms of English units completely. This is kind of a mixture metric in English. This is all English. And then there's this one that's pound mass of CO2 per megawatt hour of electricity, which is a third one. So we have these 3 EFs. And so we have to do a lot of unit conversions in order to compare ours to theirs. So looking at the units, our EF is mass of CO2 per mass of fuel, whereas EPA's, the first 2 of them, are mass of CO2 over volume of fuel. To convert, we need to multiply our EF by mass of fuel over volume of fuel, and you could see that that will give us what we want because we're going to multiply by mass of fuel and then divide by volume of fuel. So we'll get our EF in terms of EPA's units, and that's exactly what we want to do. But notice that this mass of fuel per volume of fuel, well, that's simply the density of the fuel, which in our case is methane. So that's the density, and we can calculate that density by using the ideal gas law. The fuel is a gas, it's methane, so we approximate it as an ideal gas. So P is rho RT, or rho RU over the molecular weight of, this is all of the methane, times T. So we can solve for rho is equal to P times molecular weight of the methane over RUT. And so this is the pressure and temperature of the exhaust gases. However, EPA is using standard cubic feet of their fuel. So we're not going to actually use the P and T of the exhaust, but P and T of standard conditions. So finally, EF hours in EPA's units, which is what we want, is what we had previously calculated as EF hours times PM fuel over RUT. And this is at standard cubic feet, so standard conditions, so that's the pressure and temperature we'll use. So this is actually our answer in variables, and the rest is just plugging everything in and doing unit conversions. This is a lesson in unit conversions. EF hours in EPA's units. We put our EF in with its proper units that we had before. And then this is P, I'm using this equation. So P as SATP, molecular weight of the methane, and then RU, and then T at SATP, and the rest is a bunch of units, as I said. I put all my unity conversion factors in blue here to distinguish them from the actual equation, plugging in the numbers. And so you can see these, a kilojoule is a kilonewton meter, and then there's 0.3048 meters in a foot, megagram is 1,000 kilograms, 1,000 cubic feet. We're going to say that's equal to 1,000 SCF, which is what EPA's units are. So I very carefully went through and crossed out all the units that cancel, and I end up with only the two circled ones. On the numerator is kilograms CO2, and on the denominator is 1,000 SCF. And so we can plug in our calculators and get our final EF. And I get to 3 significant digits, 50.9 kilograms of CO2 per 1,000 SCF fuel. Now let's compare to what the EPA EFs are. I scrolled back to the question right up here. EF that I looked up was 53 kilogram CO2 per 1,000 SCF of natural gas. And so when we scroll back, we see that compares very well with ours. We had 50.9. So that's actually pretty good agreement with what EPA says. So we've done this very simply with just some simple chemistry. And so let me just list some reasons for the difference or the discrepancy. Number one is that we use methane and EPA uses natural gas. Natural gas is typically, 90-95% methane, but that will make some difference with the other stuff that's in there. We also assume stoichiometric or ideal combustion, but we all know that real life is not ideal. You can say that about pretty much anything in life. And it's especially true here that the EPA is getting their EF from actual physical measurements, and we're just doing it theoretically. But nevertheless, we have very good agreement, so we're pretty happy with that. I should say first, the second one is the same units. It's just all English. So that's just a matter of unit conversions. I'm not going to show any of the work here, but you take our answer from EPA's units for their number one EF and just convert to pound mass CO2 instead of kilogram CO2, and then it's million instead of 1,000 SCF fuel. And so you can do that on your own for practice. Again, you get up to 3 digits, 112,000 pound mass CO2 per million SCF, and then compare that with EPA's value for this same thing in the same units. Was EPA's was 120,000. But again, that's pretty close. And we have the same reasons for the discrepancy. EPA's number one and number two are the same. They're just different units. And then finally, we look at the third one, and that one's going to involve a little more work. So here's the third EF from EPA. It's given in pound mass CO2 per megawatt hour of electricity. So that's a much different denominator than we had before. We're not looking at the amount of fuel. We're looking at the amount of power produced. And so that is going to involve an efficiency. So let's do some conversions here. I converted to kilogram instead of pound mass to get everything in here in terms of SI units instead of this funny mixture of English and metric. And so that's just a matter of conversion. Using 1 kilogram is 2.204 pound mass, and I get this EPA EF in terms of SI units. And then remember hours that we calculated at the beginning was 2743.3 kilogram CO2 per megagram. So how do we compare these two when they have such drastically different denominators? Well, the key would be, and this is what I'll actually calculate here then, is calculate the overall power plant efficiency that EPA used in whatever plants. They do a bunch of measurements at various plants and then get their EFs. So you know from your thermal class that we're going to be under 40% for a standard power plant producing electricity. So we define power plant efficiency as actual power produced over maximum possible power produced, or in terms of energy, actual energy over maximum possible energy. So we're going to do that one. And what we want to do then now for this part is predict the overall power plant efficiency in percent that EPA assumed or measured. Actually, these are just measured values that assumed in order to obtain this emission factor, which we'll call EPA. So I just want to find the efficiency that was used in in the actual power plants that EPA used to measure their EF. First thing we do is look up the HHV, the higher heating value. So again, we go back to your thermo class, and this would be of methane. Remember, EPA is using natural gas, so that's part of the reason for our discrepancies. But let me just define this for you. HHV, higher heating value, is defined as the maximum energy you can get by burning a unit mass of fuel, and the unit mass we'll use is kilogram. I looked this up. HHV is 55.5 megajoule of energy per kilogram of fuel, fuel here being the methane. So the maximum possible energy produced will equal HHV times the mass of the fuel, just from this definition and looking at the units. So this is what we'll use in our equation up here for eta. And let me call this equation 1. The other thing we need to know is that our estimate of our EF that we generated assumes 100% efficiency, because we assumed ideal or stoichiometric combustion, which is the best you're going to get. So this is assuming 100% efficiency, whereas the HHV is the real life value. And so we have to do a little bit of thinking here. I rewrote our EF that we had calculated, assuming 100% efficiency. Let's make an equation that's similar somewhat to equation 1, except for our EF. And so I'm going to write the mass of CO2 emitted from the above equation is equal to EF hours. This is EF hours times M of the fuel. So all I'm doing is looking at this as the mass of the CO2 emitted, and this is the mass of the fuel on the denominator, and then our EF on the left. So this is the equation that we want. And remember, this is at max possible efficiency. I'm going to call this equation 2. And now we can combine equations 1 and 2 to solve for the maximum possible energy. So let me do that here for you. First, I solve for M fuel from equation 2 and get this. And then I use equation 1, which is relisted here, and plug this in for M fuel. And so I get this equation, which I am going to call then equation 3. So my maximum possible energy is HHV times the mass of CO2 emitted over EF hours. And EPA's third EF is in terms of mass of CO2 emitted per megawatt hour of electricity. And that denominator is the actual electric energy generated, because it includes the efficiency of the power plant. So we can combine these things to get this result. Then finally, I generated equation 4, which is the actual energy generated by the power plant would be M CO2 emitted over EF EPA from this equation. And now finally we can combine equation 3 with equation 4. So here was equation 3 up here with equation 4 and our definition of eta plant, which comes from previously in the problem statement. I had typed this out. Eta plant up here is actual energy produced over maximum possible energy produced. So we have these equations here: actual energy produced, equation 4, and maximum possible energy produced is equation 3. So finally, we're just taking the ratio of these guys to get the eta, and we're almost done. Eta of the plant is actual energy, equation 4, over max possible energy, equation 3. I plug those two equations in, and you notice that MCO2 is on the top and the bottom, so those cancel out. So after all this work, we get our final answer in variable form, which is given here. The rest is just unit conversions and plugging in the numbers. So I typed that out for you, plugged in all the values from these three equations, and when you put everything together, you get 0.346, or eta plant finally is equal to 34.6%. So that was a lot of work, but it's interesting that we can do this kind of analysis just based on some simple chemistry and end up with 34.6. So the bottom line is that the power plants that EPA used to measure and calculate these EFs have an average efficiency of 34.6%, or about 35%, which seems pretty low, but that's how power plants are pretty poor efficiency overall, as you learned in thermodynamics.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.